So I'm Adrian Geisow. I'm a senior research manager in charge of plastic electronics. And you're going to ask me what plastic electronics is. Let me set the context by saying that all the products we carry around these days increasingly are all user interface. So if you have a cell phone, if you have a tablet, if you have a laptop, most of what you see is either a screen or a keyboard or a combination of the two. And increasingly the physical product is dominated by those components, the screen, the touch elements, but possibly a keyboard if you have one. And if you look, here's an old laptop we've taken apart. This is just the screen, and you can see it's quite a chunky element. It's made of lots and lots of stuff. If you feel that, it's quite a weight. Yeah. And it's sort of expensive double glazing. This is 2 sheets of glass, which is fragile. You wouldn't believe the number of laptops that get broken because people drop them or kneel on them. I don't know how many broken cell phones you've seen with where they've fallen out of pockets and so forth. So glass is a bit fragile, it's a bit heavy, and the way these displays are made is essentially like making a giant silicon chip. So they take even larger sheets of glass and cover them with transistors by quite an expensive process. It's a process of putting layers of exotic materials down. That's done at high temperatures and often in a vacuum chamber. And then those materials are patterned essentially by putting a resist everywhere, exposing the bits you don't want, etching the resist away, etching the exotic material away, and then washing off the resist. So most of the stuff that you didn't want, you only want a few wires or lines or dots. They get left behind. Everything else has been put on and then etched away and rinsed, thrown away, put down the drain. So you can see that these are heavy, they're expensive because of that process, they're fragile, they're also not very efficient. So if you look through this, you can't see through it really. That's the white state, that's when all the light's coming through, it's not the dark state. And all of this is a big backlight, and today's displays are often 90% of the light that goes into the backlight is thrown away effectively, so they're very inefficient. They're not very green as a product, impacts your battery life, have to have a bigger battery, makes the product bigger and heavier again. What could we do about that? Well, we started looking at this a number of years ago, and the first thing we thought was, well, if you didn't have to continually refresh the display, maybe you could make the whole display much simpler. Today's displays are painting the image 60 times a second. That's actually, for a complex display, that's quite a fast data rate. And speed usually means power, so that's quite another drain on power. If you see what we've got here, this is a display we made some years ago, and it's got an image on it, and the image was written actually several years ago, and it's not actually now plugged in. So here's a display which, when you turn it off, it keeps its image, so it's not burning power unless you're updating. It's not only that, it's also made on plastic, and I can take you very quickly through the manufacturing process because we've gone to what we call printed or plastic electronics, where we're trying to pattern things rather than subtractively, the way I described before, much more towards the way a printing system would do it, is additively. You only put what you want where you want it. Saves a lot of expensive exotic materials. The magic behind this display is to give it its memory, every pixel remembers its state, is that it's actually got this bumpy surface on it, and that, as I say, it's expensive double glazing. A liquid crystal display is a thin layer of liquid between 2 sheets of glass. The liquid is a bit exotic, it has a grain like wood, and that normally would just lie in one position. That grain pattern lies in one position. A normal display, you put a field on and you kind of reorient that grain to line up with the electric field. In this case, we put a bumpy surface on, and that tangles that grain up, and so there are 2 places where it wants to stay when there's no power. Excuse me. But this is a very tiny structure. This is like the kind of size of the dimples on the back of a CD or a DVD. So traditionally, you'd make that by lithography, and here's one we made earlier on a piece of glass. If you had to do that for every display, it's a bit of an exotic process. What we did instead was to take a copy of that as if you like, a printing plate, and it's now on flexible plastic. It's a copy of that original structure, if you like, made by casting a copy or imprinting a copy. And then we've metallized it so that we just have a window through the bit that we're interested in. And we can then use that effectively as a printing plate to make multiple copies almost on a continuous basis. And so here I have one of those copies made on a piece of plastic, and you can see the same sort of diffractive structure there. We can also use that to pattern other structures in the system. So this is a thin piece of metal foil, and we've imprinted structures that control where thin metal electrodes go, where red, green and blue color filters go, by then depositing into channels, if you like. So we've made a sort of complex structure there, and you can just see, well, the camera probably will find this difficult to pick up, but contact positions, very fine metal lines that go along, and this is sort of slightly coloured area is the red, green, blue colour filter array. It's probably easier to see on this. You make that and you transfer it off into transparent substrate, and you can sort of see now this is the colour filter area, these are the contacts, and this is the thing we printed previously, and our display is really a sandwich of those two put together with a thin layer of this liquid crystal material between it, and that results in this display you see here. And here's a sort of an earlier version. Now you can see this is all done in our lab here in Bristol. It's effectively made by hand, sort of Blue Peter style with sticky tape. Because we're trying to do the research, we then get that into industry. And one of the other things that's appealing about plastic electronics is a lot of these processes are potentially 10 times cheaper to make in terms of the investments you'd have to build a factory. So it's an area where new manufacturing technologies can come along. There may be much more potential for starting to make at least elements of this in Europe, in the UK, and so there's a potential commercial benefit to the UK here, and we're trying to encourage that as much as we can.
So what will this actually mean in terms of the displays on our phones or laptops?
So this is what we did. We did this some years ago, and we were trying to save power so that you would just have a longer battery life. You could have more complex images. You'd simplify some of the electronics by only having to incrementally update rather than repaint the whole screen continually. If you're just reading a page of text, you only update it when you want to change certain things. When we completed this work, people made the obvious link that we'd saved a lot of power in driving the display, but you still have to have a light behind it. So almost all displays today all colour displays are effectively stained glass windows with a red, green and blue sub-pixel which filter out the light, and then you just let either the red or the red and the green if you want yellow, or red, green, blue if you want white through. That still burns a lot of power because you have to have a big light. The red, green and blue colour filters throw away 2/3 of the light. The rest of the optics to make it work throw away another 50% at least, and then actually you can't have a completely open pixel. You have to have a border around it and so forth. That throws away even more, and that's what gives you a net result of only 10% or much less sometimes coming through the display. So we were then asked to look at, well, if you're really going to have much lower power portable products which have longer battery life, thinner, lighter and cheaper, how can you fix that problem and just use ambient light rather than having to carry a light around with you and throwing 90% of it away? So what we have here is a demonstrator. I'll plug this in of an optical effect. If you come, no, just get rid of that. So this has got no light on behind it. It's just mounted on, it's a plastic display here which is about a millimetre thick. It's just mounted on this to keep it secure, because again it's a sort of made by hand prototype, and it's cycling through. So this is not a full-blown display at this point. It's the HP logo as a sort of segmented display, so we're driving the whole HP logo shape as one giant pixel, if you like, shaped as the HP logo. We are driving each of the coloured segments that will come up in a minute across the bottom. This was to test the total sort of colour range you can get. So the only displays that currently use just ambient light are things like the e-books, which are black and white. There are just beginning to come out some colour ones, but they have the same problem, that if they have red, green, blue colour filters on the front, they throw most of the light away. So you either end up with very dark display or very pale colours to compensate for it. This is, just like printing, is actually a cyan, yellow, magenta layered display. So we're controlling each of those colours by subtractive colour rather than additive colour, which is what a normal display does. So again, a plastic display, potentially made by the same kind of techniques, now with much better optics. This is much more efficient optically, so you can get away with just using ambient light, and you can see it's actually quite bright colours under the slide.
So how would that work? You know, I'm thinking of you talk about ambient light. It's all very well during daylight hours. What about?
Well, you can, of course, like you would a magazine, a book, or a piece of paper. You turn the light on, and it's, if you need a bit of additional light, it's much more efficient. Given that this is very optically efficient, you don't need a very bright light to make it work. So that's the problem with the more traditional displays, is you need 10 times the amount of light to match ambient, and that's in office conditions. If you take your backlit display outside when it's sunny, you're trying to compete your backlight against the sun with a lot of inefficiency, and it just doesn't make sense. So this will get better as the lights get brighter. Yes, if you are in very dark conditions, you might want some supplementary light, but that would be just as you would if you want to read a magazine or a book. Or you could build in some very low power front lighting. In fact, some of the monochrome ebooks are doing that now. They have a simple glow light, just a little LED or something, that illuminates it enough in dark conditions, so it's not a problem. And then, and of course, you only need it when it's very dark, which is actually not so frequent. I mean, mostly people are operating in environments where they have 90% of the time they have plenty of light to do whatever they're doing. So what I just showed you, if you put a display which is controlling yellow light and cyan light and magenta light, they are actually absorbing red, green and blue. So that's why I say they're working the opposite way around. They're subtractive rather than additive. And we're effectively turning blue absorption off in the yellow layer. If you therefore have to stack those three layers together, you still have a loss problem, that you've got to go through a lot of layers, a lot more layers, 3 times as many as in a normal display, and you still lose some things. It's very easy for the colours to become muddy. So the innovation, what enabled us to actually have that bright colour that you saw there, is that the blue light only goes through the top layer. It doesn't go through the bottom layers. We have magic mirrors that return the light as soon as they possibly can. And we've got some samples of them here. I'll show you them on this black background. So you should be able to see there very bright red, green, blue colours. The sort of slightly magic thing is that they look perfectly diffused, like they're just sort of bright coloured paper. This is an ordinary diffuser next to it, which looks a bit sort of much less bright. And also, if you look through it, if you can see that, but it's not diffuse any longer, whereas the diffuser still is. That's why we call them sort of, there's a magic element. This enables, so the blue light comes in, gets processed by the yellow ink layer, if you like, and then immediately returned by this, and it's returned in a nice scattery way, as it would be from a scattery piece of paper. But the light that carries on through to be processed by the red and green absorbing layers, the cyan and the magenta layers of the display, is undisturbed, so it doesn't get messed up before it gets processed. And we now found a nice cheap way of doing it. You can make those in a rather exotic, expensive way, but to make a low-cost display, you've got to make this simpler. And here we've put all of that together, and we've actually made it pixelated now. So we worked with some people in the US to make a cyan, yellow, magenta display on plastic with transistors to drive the pixels, and put the whole thing together. And you can see this is cycling through, the HP logo spinning, and quite good colour. There's a little colour reference. This is a colour standard for simple printing, we're using that as a sort of reference point to compare. So this is a plastic display showing, made by Plastic Electronics Techniques, no backlight, just using ambient light. It's probably the most efficient colour display in the world at the moment, I would say.
So in terms of power usage, what are we talking about in comparative terms to a
In comparative terms, this is for a standard size, a phone or tablet display. If you take a tablet display, these days that might be consuming 5 watts. It depends on which it's between in the 1 to 10 watt range, depending on exactly what technology is being used. This could be 10, 100 times less than that, because you've thrown most of that power goes into the backlight, and that's gone completely. So it's significantly less.
And in terms of resolution of displays, because obviously in certain places they like high,
very high resolution. Yeah, this is at the moment, because as you try and get higher and higher resolution, the optical efficiency is more and more challenging to get, because there's less room to squeeze all of the circuitry and so forth. So I don't think this will hit very high resolution immediately. It will take some, like all technologies, there will be a maturity where we'd start with a lower resolution one where it's easier to do, and then roll it out. There's a bit of a win we have, because to do any particular resolution, a standard display has red, green and blue side by side. So if in one dimension it has already 3 times the resolution. And so we only need a whole single pixel. We just have them stacked on top of each other. So we have a little bit of a win there in resolution terms. But it would probably start off in the sort of just under 100 pixels per inch to get the kind of optical efficiency and the color. And then as the manufacturing technology matures, we would hope to push that towards the higher resolution. So it would start, I think, not in the front of screen, main screen thing in its first product hitting the market. It would start with secondary displays and other applications where you're less critical with for high resolution. If you think of electronic whiteboards, for example, you write on a whiteboard with a pen, the nib is several millimeters across, so you wouldn't need, to do an electronic version of that, you wouldn't need super high resolution to start with. You might want it eventually, but you wouldn't need it initially.
And in terms of sort of time frame, when do you perceive that these sort of things will be on the market?
We may be able to get some very early versions out in the next year or two. That's something we're actively working on. I can't give a definite time frame. What we're hoping to do is work with HP's partners and supply chain, because this involves a lot of people doing a lot of different, interesting technology to get it together, and that's something we're actively working on now.